Yeah, I definitely want to thank the organizers as well. It's refreshing to have a TD-specific conference and not be tacked on to an AGN one where you have to convince people that TDs are in fact real. I'll be giving a talk today on 2020 NOV, which I certainly did not vote for as my favorite, but if by the end of the talk someone wants to adopt it as their favorite, then I will support you 100%. I am a grad student currently at the University of Illinois. I work with Decker French and a bunch of other collaborators, and as part of this broader Young Supernova Experiment research group. Yeah, so 2020 NOV is not a particularly new TDE. It was discovered back in, obviously, 2020. It was found in the ZTF data stream announced by Earl. The original report, the discovery report, included that it wasn't particularly AGN-like based on the WISE color cuts. And they did find in the identification spectrum that there was evidence of both hydrogen and helium, which was promising. And so it achieved a classification of a tidal disruption event, potentially hydrogen-helium-like. And so this is the plethora of UV optical photometry that we have for 2020 NOV. So you'll notice that most of our data comes from ZTF, which is shown in the triangles. As part of the EASY group, we have also time on pan-stars. So we have the GIRZ bands from pan-stars that fill in some of the gaps here. We also had some opportunistic Swift TOOs, which are shown in the circles. We have a couple epochs before the peak, which is the dashed line, a couple after, and then a couple sort of near this, what appears to be almost a plateau after the initial fall off. With the Swift data, we also got some Swift XRT data, which is shown down here. It's very obvious that we get basically nothing initially, the UV optical peak, but we get a brightening later, about 300 days after the UV optical peak, which is quite interesting. So this gave us, some stuff to work with. So either, we're looking at sort of a stream collision with late time disk formation model, or the primary emission comes from a fast-forming accretion disk with reprocessing, kind of hiding the X-ray until late time. We're still not quite certain, so by the end of the talk, you have strong opinions one way or the other, then we should certainly chat. And so 2020 NOV, you may have noticed, was mentioned in the literature last year as part of Yvette's sort of radio follow-up survey, where they did not find any significant radio emission that they could attribute to 2020 NOV, instead just saying that it's coming from the host galaxy, from things such as star formation. So apologies to all the radio folks. I'm glad I didn't have to give this talk yesterday. So our data, right, is quite sparse, especially in the UV. So to remedy that, we developed a Gaussian process model that basically interpolated the values for our UV data to all of our R-band observation times. And we did this so that we could finally kind of develop finally fit our blackbody models to the SEDs. And so we binned the photometry into 5-day bins, and then set about just fitting our single black body, since traditionally TDEs should be well fit by a single black body. But we quickly ran into issues where a single black body was a significantly poor fit to the SED. And so we, this kind of had a knock-on effect, right? Because we wanted to also model the light curve using MOSFET. And MOSFET kind of yelled at us and, gave us some bad results that we couldn't really figure out. So then we revisited the SED. And so we stared at this for a while and figured, well, if one, why not two? So we added another black body, and it did significantly improve the fit. Of course, we don't really have a great physical understanding of why there might be two black bodies. Discussions seem to indicate that this might be possible, or we're looking at some kind of thermal tail of the broader spectrum, or some other effect that's going on here. So again, if you have ideas, I'm more than happy to hear them. And so in this case, right, we have a hotter component here and a cooler component here. Since this seemed to match more of what we might expect from a TDE, this is sort of what we've decided is our tidal disruption event, and that this is just something extra. We did try just a power law in black body, but in this case, it doesn't really help us too much since the power law kind of overtakes the blue end and we don't really know what to make of that. But nonetheless, we did score these and it did tell us that the double black body seemed to be the best for this use case, so we kind of took that and ran with it. Yeah, so this is sort of what we get out of the black body fitting. So here I'm plotting both the blue hot component and the red cool component. And you can see just from looking at the blue that it does seem to behave much like a tidal disruption event. We get a peak luminosity somewhere around 10 to the 44, which is great. Temperature around 3.5 times 10 to the 4, which is also great. Peak black body radius somewhere around 6 times 10 to the 14 centimeters, which is super awesome because that kind of matches the theme of being in a hydrogen plus helium tidal disruption event with the smaller black body radius. And it's turned out to be excellent, but of course doesn't help us explain what this is. And so this has a peak luminosity, something of an order of magnitude less, peak radius, something of an order of magnitude more further out, and a temperature around 8,000 K, which again, we're not quite sure of where that might leave us. So we take our, what we consider to be our TDE photometry, and we do the normal thing and fit some power laws to it to get the fallback, and it does seem to be consistent with your regular T to the minus 5/3 fallback, shown here. We did chop this because it does seem to be that there is a significant plateauing effect that happens about 200 days after the peak. Of course, there's even more strange behavior where at even later times we get another fall off, and then one might be another rise. We don't really cover this, and I won't be covering this in the talk, but again, if you have ideas, I'm all ears. And so so while this seems to match quite well, the plateau is, maybe something from disk emission or some viscous accretion, depending on if we want to take the stream collision model or the fast forming disk as sort of our nominal source for the peak emission. So now that we have our nominal TDE and some data to go with it, we then pump it through some of our fitting algorithms. So this is some of the results from MOSFET. In order to give MOSFET data that we think it would best understand, we actually remove the red component from our photometry before we feed in this sort of subtracted, reduced photometry to MOSFET, since MOSFET fundamentally understands only a single black body for the SED internally. And so we get pretty good fits. Again, here I should point out that we do crop the photometry right before the plateau. As Brenna had mentioned a couple days ago, MOSFET doesn't deal well with changes in the fallback behavior. So we do stop it about 59300 and have it fit there. And you can see that it does seem to highlight the fact that we do have a plateauing that occurs. But otherwise, it does seem like MOSFET doesn't complain as much as it did before. We get an impact parameter of about 1.8, which does suggest something along the lines of a full disruption. Our mass that's returned by MOSFET is something about 10 to the 7.3, and the stellar mass that's above solar at 2.3. Now, because MOSFET implicitly assumes that the emission mechanism is from accretion behavior, we did want to test the other theory of stream collisions with late time disk formation. So we feed in our peak luminosity and our peak temperature to TD mass to see what it gives us. And we find a significantly different black hole mass, about an order of magnitude less, even though the stellar mass estimated is on the same order. The uncertainties on here are quite high. And so this gave us pause. And so to contextualize the black hole mass estimates, we fit the one of our high resolution LRIS spectra with PPXF to get a sigma and just feed it through the M sigma relationship, and we find a black hole mass that is roughly consistent with our MOSFET black hole mass, so that was heartening. However, when we take the stellar mass estimated using Prospector, since we do not have a host spectrum from before the flare, we just end up fitting archival data with Prospector to get back a template spectrum and some other parameters for the host, which feeding it through the black hole mass stellar mass relationship gives us a lower black hole mass, not quite as low as TD mass, but still kind of low. We then do the same thing with the recent Yao et al. Paper, specifically for the relationship that they derive for TD specifically. And we do get something that's more in line with the M-sigma relationship and MOSFET. So we do take the sort of MOSFET as our nominal value for the black hole mass for the rest of our calculations. So that's all well good. Photometry is neat, but the holy grail of really figuring out TDEs lies in the spectra. So what does that show us? So we have about 10 spectra, 9 of which are particularly useful, and one of which I don't include here because that's just the identification spectrum. And we have a wide spread of different spectrographs here that gives us different resolutions. And here I'm just highlighting some of the obvious emission line sources here. So we have obviously our H-alpha Balmer lines, H-beta. We don't see significant O3 emission that really kind of emphasizes the wise color cuts that we had found before that also doesn't suggest an AGN activity. Likewise, the ZTF photometry historically did not seem to vary much, so we also assumed it was not influenced by any AGN activity. But perhaps the most obvious thing here that you should really take away from this is the beautiful double peak Balmer features that we find in the spectra. And you can see here that it is present quite early, right? So even at 27 days before our peak in the UV optical, we are seeing double peak structure. And this continues almost all the way down until about 1,000 days afterwards, where we find really no evidence of the peak structure anymore. So this does seem to be something like a transient disk-like thing in the spectra. And so this puts 2020 NOV in a group with the likes of 2020 ZSO or 2018 HYZ or PS18KH, which also showed some nice double peak structure in the spectra. But what should be obvious is that these are very narrow. The double peak structure is very narrow compared to what you might expect. We get widths on the order of a couple thousand kilometers per second, which is just really small compared to some of the historical version, the TDEs that we take as precedent for this type of structure. So we are struggling to figure out what to make of this. So the first thing we do is we look at the evolution of the emission features over time. So we have a chunk of 22 low-resolution Floyd spectra that was donated by Yahir and his group. And so we looked at this, some of the prominent emission sources over time. Here I'm focusing on H-beta, since H-alpha, we do not have a host spectrum, so it's contaminated by N2 lines and obviously the host narrow line emission as well. So with H-beta, at least, we can kind of get an idea of what the luminosity evolution looks like and the fold half max. So you can see even for a disk-like structure in the spectra, the fold half max is quite flat and quite low. Our luminosity also doesn't show significant evolution over time. So in red here is 2018 HYZ, so you can see how it might compare to something else that also showed double peak structure. But here on the right, I do show the SNAC spectra that really does clearly highlight that there's an evolution in the double peak structure. Dark blue is early time, dark red is late time, so you can kind of see that as we get near peak, it kind of grows in luminosity and then quickly diminishes till about 1,000 days afterwards, where it kind of disappears. And so we fit the double peak structure with the disk model described in Miraculous et al. And so we get pretty good fits, but of course we have a lot of degeneracy due to the fact that we had to include the narrow line emission from the host, and we also included a broadline Gaussian feature, which seemed to be a prominent thing to do in previous TDEs. And as you can see, that at least for the first 4, the disk is well defined, seems to kind of disappear around 155 days after peak, and then reappear a couple weeks later with a prominent blue asymmetry, and then of course disappears again about 1,000 days afterward. So then we look at the evolution of the disk parameters over time, and the most obvious thing is just how extended this is, right? So the inner radius is something 10 to the 3 RG, which is something times 10 to the 16 centimeters. Our outer radius is even further than that, 10 to the 17 centimeters, which is highly extended. We don't see a huge amount of eccentricity evolution. The uncertainties kind of bury this. So it's you know, up to interpretation. This rise is real. Likewise, our inclination is somewhere around 40 degrees and kind of stays roughly constant through time. So what does this mean when we put it all together? And so this is sort of the plot we've been staring at the most to kind of understand what's sort of happening in this tidal disruption event. So here I'm plotting both the high temperature radius derived from our black body modeling that we think is from the TDE, along with the red, which is sort of that red component that we had before, which we're not really quite sure what to make of. In orange is the photospheric radius that's derived from MOSFET, and the triangles represent the inner radius and outer radius of our disk modeling. And you can see that it's extremely extended. And the dark gray lines are sort of the theoretical maximum for the degree streams from the tidal disruption events, taken both for our MOSFET-derived mass and our TDE mass-derived mass, black hole mass. And so you can see that the disk extends far out from even that. Also included on this are these green dashed and dotted lines where we noticed in the emission line evolution that we do see a time lag for the peak in the H alpha and H beta luminosities. And so just converting that time lag into a distance gives us something on the order of the outer radius of our disk structure. We do find that there is a stratification here, which is you know, indicative of something like AGN, right, where you have the H alpha kind of furthest out, and it kind of goes down the line with helium kind of further in. But this is assuming that there's instantaneous recombination happening. So if there actually is some delay due to recombination, then obviously these lines would move inward. So this is sort of where we are at now, trying to explain what might be going on. Obviously, the double peak, or I'm sorry, the double black body fitting is an issue we are still trying to resolve. There are certainly different ways to interpret this, right? As I mentioned, there could be a thermal tail instead. Some kind of persistent disk structure might be interfering. But fundamentally, it does seem to be that, you know, either there was material pre-existing before the TDE that was just hanging out in this far radius, where the internal, which may be like fossil material left over from previous AGN activity or something else. But it seems to be that the internal portion near the black hole might be a hollowed out cavity, and that may be where the TDE actually occurs. And so this double peak structure we see in the spectra is just completely, you know, not related to the TDE, other than it may be reflected emission from the actual TDE itself. It's hard to find a relationship between both the disk and the TDE that makes sense. So again, if you have ideas, please let me know. And so with that, I'll kind of put up my conclusions. Basically, right, we have this red flux excess on the red side of the SED. Our fallback rate seems to be consistent with the TDE. We do see plateauing, which could be indications of a disk structure, either late forming or persistent. Our black hole mass seems to be well constrained, around something over 10 to the 7. Our spectra obviously are the most interesting, showing this double peak structure that does fade over the course of a couple years. And fitting, right, does seem to indicate that the disk is highly extended with an inner radius and outer radius that don't particularly make sense for something that's formed from a tidal disruption event. Our time lag analysis obviously also seems to be consistent with the disk outer radius, but of course this does assume instantaneous recombination. And so again, evidence seems to suggest that there's pre-existing rotationally supported structure at far distances, and that a TDE just happened to occur in the hollowed out cavity around the black hole. So with that, I'll end my talk.
Really cool object. Apologies if I missed this, but do you see an infrared dust echo in WISE? And if so, can you comment on what that shows?
Yeah, so we don't. All we have is sort of archival data from the host, which is why I am supposed to message Megan Masterson the coordinates for this object to see if maybe they picked up some of the infrared.
You can just look.
There is? Ooh, okay, yeah, we'll talk.
That would be cool.
Awesome.
Yeah, so thanks for the great talk. This is super interesting. Could you comment on how you ensured that you were not overfitting the data by introducing a second peak in the Gaussian process, especially since Gaussian processes are like known to overfit data?
Yeah, so we can certainly talk about this more afterward, but fundamentally we do kind of constrain the radial basis kernel that we use so that it's not overfitting variations on super small scales. And so we make sure that it's, it's always in the range of something reasonable for TDEs. What's nice is that we have really consistent ZTF R-band data, which and we only interpolate to observation times that are defined by the R-band data. So we're never interpolating in blank spaces or where we're sun constrained, where the Gaussian process has huge uncertainties, right? The other thing is that we also introduce white noise to kind of capture the systematic errors, and that does help dampen any sort of strong variations that might happen from overfitting in the Gaussian process.
Perfect, thank you.
Hey, nice talk. So I have a couple questions. First, did you detect any coronal lines? I couldn't really tell from spectra.
Not particularly, or not particularly ones we care about. Yeah, so I mean, really it's just the Balmer features that were really strong. We do see an interesting helium N3 complex, which, we talk about a lot in the paper, but ultimately decide is not from bone fluorescence or anything. But other than that, we do have some O2, but otherwise it's not really strong coronal emission.
Cool. And do you happen to remember the Balmer decrement for the 1,000 kilometer per second line?
I do not, but we can chat afterwards and I'll
do
try to dig it out
Thank
for you.
Yeah, looks like I have a comment on the red component. So it's very nice that it looks like it tracks the blue component in its amplitude.
Yeah.
So I would suspect it's just a reflection, right? Because something changes and another one completely tracks it. So have you tried? You just use set the blue component is just a black body at your black body radius, and then make a thin sheet disk, which is the pre-existing sheet, and let it reprocess. Right? And then did you try if that, which would be the simplest case? What did you? Right. And you can imagine the thin sheet can give you H alpha and so on, double peaked and so on, all those. Right.
No, I think that's an excellent suggestion. We have not done that, but I think that's probably closer to the truth than maybe what we're thinking. But yeah, the fact that these track so well is what made us think that there has to be basically empty space from the photospheric radius, the emission radius of the TDE and where it's actually being reflected. It's not going through an extra processing material or something that might slow it down.
Yeah, I mean, not necessarily a gap in the sheet. You can have your photosphere continuously connected to the sheet. You're talking about the kind of a delay time. I mean, because these are 10 to 15 centimeter, 10 to 16 centimeter.
Right.
The amount of delay is small.
Yeah,
so
yeah, exactly.
That's why they track if you dig deeper, maybe there is some delay that you can measure in the redder bands.
Yeah.
Right.
Yeah, we'll definitely check that out because I think that's a great way to think about this.
Oh, okay. I think I see iron 10 in your spectra. Call me an observer, but I mean, it's like a little bump, but I think I see it. So, especially on your plus 153 day. So just something to think about. Could be that too.
Yeah, okay. Great. I know.
Thanks for the nice talk. Could you show the light curve again with all the bands, like the real data? Yeah, I was just curious. So yeah, all the I-band data, excuse me, the I-band data, which is driving this excess, that comes from a different telescope than ZTF, right? So of course you have reference images there, so everything is fine. But if this is a pre-existing AGN and it was accreting a little bit, it could change. So you would have two different baselines that you are subtracting. So how good is our handle on the pre-flare variability that we can exclude that? Do you think that's reasonable, or it's not a systematic?
Yeah, we can certainly revisit the pre-flare variabilities. Because the pan-STARRS data where we have the I-band data, we don't have pre-flare photometry for, right? We only have pre-flare photometry in GNR from ZTF, because that was the only thing that was looking at this object before the flaring happened. Oh yeah, it could be in 3π. Yeah, sorry. But yeah, I think that's a good point. We can certainly look at that just to double check to make sure there isn't variability before the flare.
Okay, right. So yeah, that GPC1 that definitely has a different baseline than the CTF in temporal baseline. Yeah,
yes.
Too. Okay.
Yeah.
Thanks.
Just following that, another way you could check if this is what's happening or not is with LCO I-band data, which we have a ton of and are happy to give you.
Great, problem solved. All right.
Comments over.
Thank our speaker again, please.